Swayam Prabha. Digital India. Educated India.
Okay, so now we have seen 3 principles so far. There are 12 principles. I will quickly go through. The other one is designing a safer it doesn't work. Safer chemicals. Okay, so what it means is, suppose for example, there are something in the somebody is from this sea coastal area. Okay, they will understand this problem. See, it's not that the chemicals, whatever the materials you synthesize, is not only good for you, it's good for other other lives also. Okay, that's very important, and they should not be toxic to them also. Again, that is one of the sustainable development goals, right? It's not that only like humans will be happy, but other lives also should be happy. Okay, so otherwise you will not be achieving your sustainable development or sustainable society. Excuse me. Efficiency, okay, that more or less same thing. It's a different context people use. Okay, that's a property, like a more efficient way. Okay, means the whatever preserve efficacy means it's a required property. You just keep it the optimal level, whatever you want. Don't compromise on that. Again, every time I'm emphasizing, you should never compromise on your requirements. While keeping that, make sure that it doesn't have other toxicities. Okay. So this is biofouling is simple. It's accumulation of microorganisms in plants. See what happens in the sea when you have lot of people go for fishing with using metal boats and all. So it's after all a metal. So when sea water or even any water, so when this is keep on exposed, it will get rusted. Okay, slowly it decomposes. So just to prevent that, they use some paintings. Okay, the outer paints they use and they coat the material and they use. So what happens is a lot of paints earlier, whatever they used to have tributyl tin oxide. This is this one. Whether you guys know or not, tin is a very dangerous element. It does actually a lot of radical reactions. Okay, it doesn't stay quiet. If it goes, that's why it's a poison. If you just take a tin, it's as bad as your cyanide. I'm telling you. Okay, it does reacts everywhere in the body, any reactants, because it's the radical reactivity and it collapses all our body, biological systems. So it's a poison, and these are the component people are using in those paints, whatever the coatings. So what happens when they are going every time, it starts leaching, releasing into the water. And over the period of time, people found this, because of the tin, lot of sea lives are getting affected, dying. And if it's not that they are dying, you just catch them and you just bring it here and you eat. It's getting into the human body also. Now the cycle is coming. It's a bigger problem. People have noticed that is coming because mostly from this one. Okay, because it's diffusing into the water. So what people have found is there is an organic molecules which does the same job as the tributyl tin oxide. And where from this organic molecule comes? From nature. You have plants, many sources, okay, animals, waste or algae, anything. All the natural sources only. So from the natural sources, they isolate these molecules and you can be used as good as your tributyl tin oxide. Same properties they also exhibit. So now people start mixing these chemicals into the paints, okay, the coats, and they start coating. So now you may be asking, sir, if this molecule diffuse into water, there is no problem? Yes, absolutely no problem. Why? I will tell you. Anything you get from a nature is very smart and it has its own key also. When it prepares one small molecule or larger molecule, it also has a plan to how to decompose that molecule. It has. Only thing, we are not able to get the data from the nature. Always remember this. Remember this statement forever. Okay? Nature, anything you get from nature, it has a formula to decompose it. So what it means is, if this compound is there, it's coming from nature. Okay? And now if you throw this compound into the nature, throw it on the roadside or anything, it's not going to be toxic at all. Because environment knows how to handle it, how to decompose it, and the building blocks, the products, when it decomposes into small molecules or elements, and it knows how to handle it. And because they are coming from the same source, they are, at the end of the day, they are going back to their original source. It's not a toxic at all. You understand? So that's what, if you use a materials from a nature and for your purpose, it's always safer. That's why these days you see that when you go out to the shop shopping, you see the carry bags here, I am not a plastic. Why suddenly it looks like 100% like a plastic cover only, the which you are using earlier about 3-4 years back. Purpose is same, but it's written like I am not plastic, I am biodegradable, all this. What it means is the material used to make these plastics, the covers, is actually coming from a bio sources, natural sources. So even if you throw this plastic into environment, after rain or sunlight, it changes its chemical properties, decompose. The building blocks are actually going to the nature, which came from from nature only. So there is just you are taking and adding, that's all, nothing else. There is no toxicity at all, because nature knows how to handle it. That's why these materials are now non-toxic, becomes non-toxic. By biodegradable means non-toxic. Most of them will come from bio-waste actually. I will show you a few slides also. So likewise, here also people are opted. So there is no change in the property, but now the side effects are minimized. Okay, that's how you should design. Okay. Another one is safer solvent and auxiliaries. What is so special about solvents? If who is working in my lab, did you see any reactions they like lab mates performing? They use a lot of solvents. See, we use only milligram scale reactions, and and we use about 100 milliliters. ml means 100 milliliters per 50 milligram scale reaction. Just imagine industry. In the same proportion, you are going to the industry, and the same material industry is preparing in a tons scale. How much solvent they are supposed to use? And what happens to that solvent at the end of the day? And that much solvent is thrown into the environment. Is it safe? Right? So maybe you see, you people have not exposed to the vapors, right? If you go to the lab, you feel that solvent smell the first day or first few days. I don't get that. And none of us get, because we are saturated. So which means you are actually keep on inhaling that. And just imagine that bulk solvents industry is using and throwing. Okay, and there is no proper mechanism to decompose. Then how much danger it is. We will keep on inhaling. Any external object into the body is a poison, remember. It is a small molecule, small atom, large molecule, doesn't matter. Any external object, chemical entity into the body is a danger. Because your body doesn't know how to handle it. Okay, so that's why the saving the solvents, okay, are using a safer solvents which is having a lesser toxic properties, or better not to use the solvents is the good approach. Solvent-free synthesis. You try to adopt a synthetic methodology where solvent is minimized or no solvent is used. That is the ultimate. Because it's not that only academic scale reactions, because to make the proper materials what we want, every day industries use millions of tons of materials they synthesize, and they need many millions of liters of solvents, different types of solvents. So try to avoid that. So what are those? Usually people use organic based solvents. Dichloromethane, ethyl acetate, hexanes, benzene, different organic molecular solvents, and they have a lot of toxic properties. Most of them are volatile. Okay, that's how you get the smell, because the solvents are getting into the vapor state, and that's how you are inhaling actually. Okay, so they are vaporized, and at high temperature reactions you can use them, because there is a lot of vapor pressure is that they will blast out the reaction reactors, and lot of them if you inhale, for example methylated benzene, they are carcinogenic. So benzene, once it gets into the body, it starts reacting into your DNA. Okay, so they disturb the DNA structure. So lot of, not only that, many solvents, the traditionally used solvents have a lot of problems. Since we did not have alternatives, people are using. Now there are a lot of alternatives come up. Okay, so you can see that ionic liquids, supercritical carbon dioxide, you can say supercritical fluids, SCFs, you hear about it. Supercritical fluids. Water you can use as solvent. Lot of chemistry is developed using water. And there are other fluorinated solvents. So it's not that these solvents are an ultimate solution to our traditional solvents, but some places you can replace the organic solvents by these solvents. Yeah, I will come. So for example, a high temperature reaction is there. Okay, so if you are talking about a reaction at 100 degrees or 150 degrees, you will use some organic solvent in that. As I told you, the organic solvents are vaporized. So they will create a lot of vapor pressure. Though you seal it, cool it, whatever it is, the vapor pressure will be there. Even little bit less attention or use a temperature raise, you see that sometimes a lot of accident happens. They will blast out because of it. It happens. Okay, no problem. So then how do we avoid that? So there are ionic liquids which doesn't have a vapor pressure. They are liquids, but they have very high boiling temperatures. So you can use them. Ionic liquids in place of organic solvents, and you perform the reaction 150 degrees, 100 degrees. No vapor pressure at all. No need to even cool down also. If you are go to my lab, if somebody is setting up at like 100 degrees, they will use a condenser and a chilled water circulation to condense the vapors back. Okay, but now if you are using ionic liquids, you don't have to use the cooling at all because they doesn't even vaporize the solvents. You understand? So that's what. So you need to know when to use what. Okay, it's not that ionic liquids are the ultimate solution for organic solvent. No, they in some places you can replace them. Likewise, water can replace in some places. Okay, even supercritical fluids can be used in some other applications. Okay, so you should know, you should have the knowledge of each types of solvent, and whenever choice is there, you replace organic solvents and utilize them. Okay, so these are some of the greens. So that's why we call them as the alternative solvents. Alternative to what? The traditional organic solvents. Yeah, you ask. Yeah, ionic liquid is as simple as your sodium chloride. Okay, it's an ionic structure, it's a salt, but it is actually a liquid at some temperatures. Yeah, it's a molten liquids you will say, okay. So molten salts is called. So they're salts as simple as. So the only problem is, so mostly we will represent, okay, N4. So it's not that only nitrogen based ion liquids, but in lot of other ion liquids, but general structure. So let's say like ammonium salt. Okay. That means 4 R groups are there on the nitrogen. That's why it carries a positive charge. There is a counter ion, ammonium chloride. So where all the protons are replaced by non-proton protic groups. As simple as that. It can be. So the problem, and not necessarily all 4 of them should be same also. It can be different 4 groups also. But this is the base, one of the structure, ion liquids. So they will be a salt. So you see that sodium chloride Na plus Cl minus plus minus. Okay, but they are not solids. So generally they will be a liquids at room temperature. So they will be called as a room temperature ionic liquids. And any kind of salt which is a liquid less than 100 degrees usually we will call as ionic liquids. Ionic structure which is a liquid, okay, in the below the 100 degrees. We will be calling as ionic liquids, and some of them will be by even room temperature, so they will be liquids, which means you don't have to even heat it.